Yesterday and today we spent some time talking about the force or the push or the pull acting between two objects with mass. In other words, we talked about the effect on something caused by something else, the effect on you caused by the earth, the effect on the earth caused by the sun, the push or the pull on an object due to something else. Let's say that we have this pen, this board marker, a certain distance above the earth, let's say 1.5 meters above the earth right now. That's where it is, 1.5 meters above the earth. We could easily calculate the force of gravity acting on it using m times g, or using gm1 m2 over r squared. There is a pull caused by the earth, and we can find the value of that pull caused by the earth. But what happens if I take that pen away? What happens if I put it in my pocket or put it over there? What's the force of gravity acting on that spot where the pen was? What is it now? That spot right now that I'm pointing to, what's the force of gravity acting on it? Zero. There is no push or pull on that spot because there's nothing to push or pull. But has gravity disappeared? No. We talked the other day about the curvature of space-time. The Earth dents the fabric of space-time. It causes a curvature in the fabric of space-time. That's still there, whether the pen is there to toboggan down the curvature of space-time or not. The curvature is still there. Gravity is still there, but there is no force of gravity. We need another way of describing gravity beyond a force, because sometimes there is no force, sometimes there is no push or pull, but gravity itself is still there. We're going to use the term gravitational field to describe gravity. This can describe gravity in the presence of something to feel the force, in other words, to experience it, but it can also describe it in the absence of that thing, that board marker or whatever it is experiencing the force. A gravitational field is a region in which a force can be experienced by an object. It doesn't mean that there's an object there that's experiencing that force, but it's a region in which there could be a force there if there was an object to experience it. It shows the influence of a mass producing gravity, even if there's nothing to be influenced. When I put that board marker, again, 1.5 meters above the ground, there is a gravitational force experienced by the board marker because there's a pull on the board marker caused by the Earth, but there's also a field there, this region in which there could be a force, this influence of the Earth causing the gravity. There's a force and a field there, but if I take the board marker away, the force is gone because there's nothing being pulled anymore. But the field isn't gone. The field is there no matter what. As long as you have something to cause it, the field is there. In order to have the force, you need to have the field, the producer, the thing that causes it, and something to experience it. So to have the field, you need the Earth. To have the force, you need the Earth and the board marker, the producer and the experiencer. Now, of course, if we're talking about these fields, they've got to be either a vector quantity or a scalar quantity because there's a direction associated with the influence. They influence things downward. It's a vector field. If you put a mass in the field, the mass will experience a force in the direction of the field. The mass will experience a force downward. If we had a scalar field, like we could say a light field, light influences us, but not in any particular direction. Light would be a field, but it would be a scalar field. Gravity is a vector field because it influences things downward in the direction of the field in a very particular direction. All right, let's give you a couple equations that describe this now. We have, of course, the force of gravity equal to G M1 M2 over R squared. This is not gravitational field, but rather gravitational force. But it's closely related to the two equations that we're going to see in just a moment here. The gravitational field equation, or one of the gravitational field equations, looks like this. Little g, the magnitude, that is, of little g, is equal to big G times m over r squared. This is what we call the producer equation. We call it the producer equation because we use it when we have information about what causes gravity, but what produces gravity. Big G, of course, is 6.67. R is the distance from the center of the producer, what's causing it, to the point where you want to find the field. And M is the mass, but specifically, it's the mass of the producer, the mass of whatever causes the gravitational field. Sometimes you have the mass of an object producing the field, and sometimes you have the mass of an object experiencing the field. If you want to find the field strength and you're using this equation, let's make sure you're using m of the thing that causes the field. Even if you're given two values, use the one that's the mass of the producer. But there's another equation as well. This one describes the gravitational field strength experienced by something. We call this the experiencer equation. When you know something about what causes the field, you want to use the first one, the first green one, that is. When you know something about what experiences the field, if there is anything experiencing the field, remember, in order to have a force, you've got to have something to cause it and something to experience it. But to have a field, you don't actually need something to experience it. There doesn't need to be anything there feeling it. There's a gravitational field strength right in front of me, even though the board marker isn't there to experience it. But if there is something there to experience it, we can find the value of that field by using the experiencer equation. F would be the force of gravity felt by the experiencer, or the force of gravity experienced, and that would be in newtons. And M would be a mass again, but not the mass of what caused the field. This time it would be the mass of the experiencer. So we keep going back to this Earth/board marker analogy here, or example. If we have the Earth and the board marker 1.5 meters above the Earth, and we have information about the Earth, then we would use this equation to solve for the field strength. If we have information about the board marker, the thing that experiences the field, then we would use this equation to find the field strength. If we have information about both the Earth and the board marker, what are you going to do? Well, if you have information about both the Earth and the board marker, you could use the blue one, but only if you're looking for force. If you're looking for field strength, you got to use one of the other two, and you know what? It doesn't matter which one you use. The field strength 1.5 meters above the Earth caused by the Earth is the same as the field strength 1.5 meters above the Earth experienced by the board marker. So if you have information about both the board marker and the Earth, then it doesn't matter which one you use. Okay, whatever one you want. Probably this one, actually, because it's a little bit simpler. It doesn't have a squared in it. Okay, but in the end, it doesn't really matter. Now, Bruce, you're right. If you were looking for the force of gravity on the board marker, then absolutely you'd use this one. But if you're just sticking with field, you'd use one of these two. It really wouldn't matter if you know information about both of them. I'm going to show you one quick little thing off to the side. You don't need to write this down if you don't want, but I just want to show you how these are all related to each other. The board marker experiences a certain field that's caused by the Earth. So the field experienced is equal to the field produced, right? The field experienced by the board marker is equal to the field produced by the Earth. Agree? we get two different masses here. So let's call this one the mass of the experiencer, and let's call this one the mass of the producer, because we want to keep them straight, right? No, don't want to get them mixed up here. Let's rearrange this. If we take the ME up by multiplying, what do we end up getting? G times the mass of the producer times the mass of the experiencer over R squared. Well, and behold, when you combine the producer equation with the experiencer equation, what do you end up getting? The gravitational force, Newton's law of universal gravitation. Okay? All right. Just a table here that gives you some masses of planets, because a lot of times we're dealing with these questions. We're going to be dealing with planets or moons or stars or whatever. So table that clearly you don't need to remember. Any information you need on this table, you're going to be given on a quiz or a test. Okay. Also the radius of each of those planets, because that becomes useful a lot of times as well. Let's take a look at the example on 4.5, keeping in mind that we can get data for this question by going back to the table that we just saw. 4.5 says, to calculate the magnitude of the gravitational acceleration, what was the symbol for gravitational acceleration, you remember? A. Any acceleration is A, but specifically gravitational acceleration was, remember it was 9.81, right? Sometimes we calculated the value of the force by saying, gravitational force by saying m times, sometimes they said ma, but sometimes they said m times g. So gravitational acceleration was g. Wait a second. Gravitational acceleration was g. Gravitational field is g. It's the same thing. Okay, sometimes we're going to talk about the gravitational acceleration now. We're going to call it something different, gravitational field. And the reason we do that is because you think like right now, the gravitational acceleration experienced by this board marker is 9.81, right? Is it accelerating? No. So sometimes it makes more sense to talk about it in the context of a field as opposed to an acceleration, but it really is the same thing. So when the question here asks you to solve for the gravitational acceleration, we can find the gravitational field. It's exactly the same thing. So let's do this here. The gravitational acceleration or gravitational field strength at the equator of the surface of the Earth and the Moon. There may be something experiencing this field strength on the surface of the Earth and on the surface of the Moon. In fact, in the picture, it looks like there's a person, a really big person, a really tall person on the surface of the Earth and the surface of the Moon here. Do we know anything about that person? Nope. Do we know anything about the Earth and the Moon? If we look back to the table, we do. So what are we going to use? The producer equation or the experiencer equation? The producer, because we know something about the Earth and the Moon, and it's the Earth and the Moon that caused the field. So let's use the producer equation to find the gravitational field strength caused by the Earth. 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.97 times 10 to the 24, and that is on that table, divided by the radius of the Earth. I think it's 6.38, yeah, times 10 to the 6. 6.38 times 10 to the 6 meters. And we got to square that. So let's calculate that now. What do you think you're going to get here? What do you think you're going to get for the gravitational field strength caused by the Earth at the equator? Take a guess. Somewhere around 9.81, right? Let's say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by, let's use some brackets here, 6.38 times 10 to the 6. And let's square that, and we get 9.78. Pretty close, right? 9.78 meters per second squared, or we could say 9.78 newtons per kilogram. Now let's find the gravitational field strength caused by the Moon. Expect it to be bigger or smaller than the gravitational field strength caused by the Earth? Probably smaller, right? In fact, it will be smaller. Remember, if we knew information about this person experiencing the field, we could use the experiencer equation, but we don't. We do know information about what's causing it, so we'll use the producer equation. Once again, 6.67 times 10 to the minus 11, because that's the same anywhere in the universe. The mass of the moon, I don't remember that. The mass of the moon is 7.35 times 10 to the 22. And the radius of the moon, the equatorial radius of the moon is 1.74 times 10 to the 6. And we got to square that. We should expect to get a number that's smaller. Let's just double check that. 6.67 times 10 to the minus 11 times 7.35. Times 10 to the 22, divided by brackets 1.74 times 10 to the 6, and let's square that. We end up getting 1.62. Yeah, so it's quite a bit less, right? Now we want to find the ratio of G Earth to G to the moon. We've calculated both of those values. How do we find a ratio? Let's subtract. Subtract will compare to some degree, but it's not a great way of comparing. Let's divide. Yeah, let's divide. Okay, let me give you another example of finding a ratio or compare. Compare means the same thing as ratio. Okay, when you ever see the word compare, it means find a ratio. So how do you find a ratio? Well, you divide. Why do you divide? How old are you? 16? Most of you guys are 16, right? Let's assume for a second that I'm 32. Okay? I may be 1 or 2 years older than that, but let's pretend that I'm 32. You could compare my age to your age by subtracting, right? You could say, oh, he's 16 years older than I am, right? Yeah, that's a valid comparison, but it's not a great way of comparing. And why isn't it a great way? Well, because when you're 1 and I'm 17 and I was 17, then I was also 16 years older. But boy, it sure seems different, right? 17 and 1 compared to 32 and 16. Like, we're both almost adults now. Right? When you were 1, you were a baby, and I was 17, I was almost an adult. What about when you're 40 and I'm 56? Well, there's not that much difference at all, right? We might be playing pickup hockey together, for heaven's sake. Okay? You might be the guy going to get the AED to save me from a heart attack, but what about when you're 90 and I'm 106? We're both going to be in the same home together. There's not that much difference at all. We don't want to subtract to compare two things, because when you subtract, you get 16, no matter whether you're 1 and I'm 17, or you're 90 and I'm 106. The better way of doing it is dividing. When you're 1 and I'm 17, then the ratio of my age to your age is 17 to 1. When you're 16 and I'm 32, the ratio is 2 to 1. It seems a lot closer, right? And the ratio shows that. It's 2 to 1. When you're 90 and I'm 106, well, then the ratio is like 1 point something to 1. Shows we're almost the same age. And we are almost the same age, even though we're still 16 years different. You want to compare, you want to find a ratio. And when you want to find a ratio, you're going to divide. So let's do this. For question B, let's just simply divide 9.78 by 1.62. And I think when we do that, we get about 6. Let's double check that. 9.78 divided by 1.62. We do. We get 6.04. So the ratio would be 6.04 to 1. Just like the ratio of my age to your age is 2 to 1. 32 divided by 16 is 2. The ratio is 2 to 1. 9 divided by 1.6 is 6. The ratio is 6.04 to 1. All right, let's give these questions on page 218 a whirl, please.